And I'm going to introduce this by going back to the island of Guam, where I went to high school. Right off the cliff from our house was the most beautiful beach on the island. And there was a little road that would wind down that cliff, and that's where we went every day after school. I imagine that I'm there often. When you go into my office and I'm smiling, that's where I am. So suppose I go back there, and for whatever reason, I pick up a boulder. It's very heavy, and I'm walking across the sand. Oh, that's hot. Towards the water. And now I get into the water. That feels cool. That's nice. And as I go deeper in the water, it's up to my knees. I go deeper still, and suddenly I become stronger. As I go deeper in the water, the boulder is lighter because I am gaining strength. What is happening? How is this water energizing me and giving me the strength to lift this boulder?
The water's pushing up on the boulder.
Yeah, the water's pushing up on the boulder. There's the water. That's what boulders look like in Guam. They're very regular. But the deeper you go in the water, the bigger the push. That's what that equation was all about that we've been using. Now, if I take all the push from the water, I think you can see that the left is always going to cancel out the right. Okay? What's not going to cancel out is the upward push on the bottom and the downward push on the top. Because the bottom of my boulder is always going to be deeper in the water, it's always going to have a bigger push. And so that means I can add up all of these pushes by the water. I can sum them all together into one force that always points towards the surface of the lake. We call it the buoyant force. Now, you'll notice that I don't put any subscripts on it, by the water, on the block, because the buoyant force is always by the water, on the block. You know, we've already got a subscript buoyant, so I don't bother with the others. Now, here's the big question. How do I figure out how big that buoyant force is? And the person that answered this was Archimedes. Now I'm going to do this a little bit different than Archimedes did. I'm definitely going to use different language. But the idea is his. He was the genius that came up with this derivation of how big the buoyant force is. Now I'm going to take a boulder that's 1 meter by 1 meter by 1 meter. And I'm going to replace that boulder with a Casper box. Now you remember Casper the Friendly Ghost. How many of you watched that when you were kids? Okay, yeah, he was a friendly ghost. That's why we call him that. And every now and again, in a scuffle that he had, he would accidentally swallow water. And you'd see that he'd be like a fishbowl and he'd have water inside it. So this box, made out of Casper material, holds stuff. But it doesn't have any mass. It's not a wooden box. It's not a metal box. It's a Casper box. It just holds stuff. Mentally. Okay? Now, if I fill that box with water, there's going to be a weight force associated with that Casper box filled with water. Now, I know that the density of water in MKS units is 1,000 kilograms for each meter cubed. And by golly, my Casper box is 1 meter by 1 meter by 1 meter, 1 meter cubed. So there's 1,000 kilograms of water in there. How much does it weigh in newtons? Not hard. Yeah, 10,000. Just take M times G. 10,000 newtons. And here's where Archimedes' genius came in. He said, you know what? That water in the box doesn't know that it's special. It doesn't know it's different from the other water. And so that means that if I let the box go, it's not going to go up, it's not going to go down, it's going to stay right there. And that means that the buoyant force on that box has to be exactly 10,000 newtons. And then Archimedes went further and he said, I could put anything I want in that box. What if I put steel in that box? Well, if I put steel in that box, I'm going to have a much bigger force, weight force, than 10,000 newtons. Turn to Nimrod, your neighbor, and explain why that would be more than 10,000, and use the word density. Use the word density. Okay. I hope what you said to Nimrod was, steel's more dense than water. In fact, it's 7.8 times as dense as water. And so that means the weight of the steel in that box is going to be 7.8 times greater than that of water. It's going to be 78,000 newtons. However, the buoyant force is caused by all the water surrounding the box. It doesn't care what's in the box. The water surrounding the box pushes the same regardless of what you put inside the box. And so that means the buoyant force is still going to be 10,000 newtons. And this box of steel is going to accelerate down to the bottom of the lake. Okay? If instead we fill that box with styrofoam, the weight force is going to be less than 10,000. Why? Because the density of styrofoam is less than that of water. But the buoyant force just doesn't care what's in the box. It's still 10,000. And that means this block of styrofoam is going to accelerate up towards the top, and it's going to pop up out of the lake and float. Now, I love the far side. This one's a little dark. Embedded in styrofoam shoes, Carl is sent to sleep with the humans. Poor guy. Okay. So, this is Archimedes' principle in a nutshell. The buoyant force acting on an object is equal to the weight of the fluid that's displaced by the object. Another way of thinking of that is the weight of the fluid that would fit in the Casper box. As a consequence, if an object has a greater density than that of water, it will sink in water. If it has a smaller density than that of water, it will float in water. And that's what you learned in the 3rd grade. And it seems so simple. And yet I'm going to show you a problem before the end of this hour that is going to be just hard. Way hard. And you'll, I hope, come to respect these problems.